Okay, good morning and welcome to this seminar. The seminar of today will be given by Isabel Rebollido from Universidad Autónoma of Madrid. Thank you for coming. The topic of this seminar will be the detection of exocomets, the gaseous environment of main sequence stars. And just a brief introduction of Isabel. She made the physics career in Santiago de Compostela, then she moved to Canary Island, to ISC, to make the master there. And now she's doing the PhD and almost finished in Madrid, in the Universidad Autónoma, on the topic of gas around the stars. And this is the main subject of this seminar. Absolutely coordinated with the discovery of a new exo object coming from outside the solar system that was discovered yesterday. So it's a exocomet, local exocomet now, a Wamamuma, a new one. So I think this topic of this seminar will be really interesting. Thank you, Isabel, for this seminar.
I hope you hear me well. If not, let me know. So I'm going to talk about exocomets, which is basically the same as comets, but in other solar systems. So while planets are now routinely detected, and we have around 4,000 or even more, we know very little about small bodies in other planetary systems. So this study tries to get a bit closer on those objects that tell us a lot about the dynamics and the composition of these systems. So when a planetary system forms, we have initially a lot of material around it. It's mostly gas. We have very little dust, but with time, this gas clears. So this would be the initial stages of planet formation. And while the disk settles, we start to form larger particles of dust, which eventually become debris. And the gas in the disk, most of it, or sometimes all of it, it's blown away or accreted into a star. So we end up with a disk of debris, which is mainly dust and some larger particles, bodies that will end up being planets or the small bodies of the system. So it would be something like this. But there should be no gas in the systems, just the remains of the planetary formation, which are these larger bodies and dust. And the usual way to detect this kind of disks was by means of photometry. So we found excesses in micro-wavelength ranges that told us that, well, this is clearly apart from the stellar photosphere. So this told us there was material around the star that was colder. And so in these disks, there should be only dust and small particles or growing up planetesimals. But we found recently that there's actually gas in a lot of these systems. This is images from the submillimetric regime, but we also find it in millimetric and infrared. So these are both systems that host a bright debris disk, but when looked in other wavelengths, they also show that there is actually a lot of gas in the outskirts of the system that is cold. So where does this gas come from? It could be from two main sources. So the first one is that comes from a protoplanetary origin. So it's the remains of the formation process. But this seems unlikely because just the radiation of the star should blow the gas away. So it's more likely that there is a secondary origin, that it's somehow the gas is replenished by several processes, for example, the evaporation of icy bodies, which would be similar to what we call the comets or the exocomets in this case. But it could be also collisions or outgassing of other bodies. But what we also see is that this gas is not only in the outskirts of the system, but it's also inside the system, very close to the star. And we see that by means of optical spectroscopy. For example, these two cases are also two debris disks, very bright debris disks, that show in the bottom of the photospheric calcium K line, so a metallic line, conspicuous, let's say, absorption, narrow absorption, that it's very stable. It barely changes in equivalent width. So that means there is gas that it's very close to the star. Would be these two. And we see that in quite a bunch of debris disk, but we also see that there's other types of gas. So this is again the photospheric calcium 2K line. So this would be 3,900 angstroms. And we see the stable absorption that tells us that there is gas very close to the star that barely changes in equivalent width. But we also see that if we look at it in different dates, there are other absorptions, usually redshifted, that appear in the calcium line. So the physical explanation for this, when it was first detected already in the 87, was this. So these absorptions we see sporadically are the tails of the exocomets passing by the star. So bodies that are sublimating or evaporating a lot of material. And we expect these bodies to be just like comets in the solar system. So they maybe have as well two tails, so a gaseous one and a dusty one. And the dusty one we don't see in spectroscopy, but we can see it in photometry. And actually, it was predicted in '99 by Le Cavalier de Setans that if we see a comet transiting in front of the star in photometry, we would see a shark fin shape. So this would be the solid nucleus of the body passing in front of the star, and this would be the tail. And we do see sort of variations in photometry that could be related to comets. So there's a bunch of white dwarfs that are very polluted. They have a lot of metals in the surface and the atmosphere, and that those metals should sink very rapidly. So apparently there should be something replenishing those metals. And they also show, when observed in photometry, irregular dips that are not periodic, that could be related to the presence of comets. And it's not only in white dwarfs, but also the famous Voyaging star has these dips that could be related to the presence of exocomets. And a couple of years ago came this discovery that was published last year, where we can clearly see the fin shape, the shark fin shape here. So this was came out as the first discovery of exocomets in photometry. And this was the big exocomets in photometry paper that came out just this year, because Beta-Pig, the star where exocomets were first discovered, had also exocomets in photometry. And well, you can see that the duration of the exocomet is quite different than the ones we see in spectroscopy. I will tell you later, but this is about 2 days. So if we see the dusty tail in photometry, that means the one we see in spectroscopy is the gas, right? So this is an explanation of how these absorptions vary. So we're looking from here, and when the body crosses our line of sight in front of the star, and it has a tail, we don't see the solid part, but we see the gas crossing, and this would be the calcium 2K line, which is the line where everybody looks for exocomets, and the H line, which is the other line of the doublet. And if they are very deep, or if the gas is optically thick, you can also see it in that line. So this is a movie of how exocomets vary in Beta-Pig. You see mainly in the red part that there are a lot of variations, but also sometimes in the blue part. So that would be tails of exocomets transiting in front of the star. This would be all of them plotted together. And this is another movie to show in both lines. This would be the K line. This is the main line we use, and also the H line. But you see the exocomets are more or less the same in both of them.
But why exocomets are not simple planets crossing the line of sight?
We call them exocomets because they evaporate. Okay. It's comet-like object. Yeah. So all this Beta-Pig spectra, these are from Beta-Pig Taurus. So the star where exocomets were first found were published by Flavien Kiefer 2014 in a Nature paper, where they could use the information from all of these spectra. I think he used 2,000 to find that there's actually two families of exocomets in Beta-Pig Taurus. because of their velocities and depth of the observations and so on. And it was consistent with the main picture of a planetary system, with a perturber, because if we have small bodies, we expect large bodies as well to be present. So a perturber will interact with material in the outskirts of the system and throw it inwards. And a couple of years before a Kiefer's paper, already a planet around Beta Peak was found, consistent with predictions from exocomets. And so, well, the first report was in the 87. It was Beta Peak. It's a super well-studied star. But now we came to around 25 stars with exocomets. So we don't have a lot of information on them. And in spectroscopy, they're all around A-type stars. So there's possibly one exception. There is this one, that it's an F2. It's also 1.4 gigayears, so we shouldn't expect much activity in stars that old or in systems that old. But this is only this is the variation, and this is only a 2.9 sigma variation, so it's not clear. So we definitely need more data in the field. So our project starts here with very little stars with exocomets reported, and we constructed this sample, highly biased towards finding exocometary material. So we chose stars where a debris disk, a bright debris disk was present, because that means there's material around it, right? And also stars in young associations, because when you come out of the protoplanetary phase, there's probably a lot of dynamical interaction in there, so more likely to see exocomets. We also chose in our sample all the stars with FEBs, falling evaporating bodies or exocomets, and stars with presence of either hot material close to a star or gas. And we also chose some Lambda-Booty stars because they have anomalous abundances that could be due to the activity of the bodies in the system. And so we have 117 objects. We observed all of them. And that can take us to monitor FEBs and detect possible exocomets in all the other groups. So that was the main objective of the project. But I have to say that Beta Peak is not included in the sample because it's already so well studied. So this is how our sample looks in the sky. We didn't choose any preferential position, but we have, for example, here a group of young stars because they're all in the same association. And we have a lot of stars in the south hemisphere, but yeah, more or less. There's no clear preference. So this is the facilities we used. We used 2 in La Palma, 1 in Chile, and the one in Mexico was used remotely. And we ended up with over 2,000 high-resolution spectra for this object, for these 117 objects, along 2 years of observations. So what we did with all that data was construct a time series data for the objects in our sample in order to detect variations. For example, this one star has some variability here, which we would call exocomet-like variability, or falling evaporating bodies. But we also investigated the stable absorption, this one, in order to discern whether it comes from the circumstellar or the interstellar medium. So first thing we did was to check the radial velocity of the absorption, if it matched either with the radial velocity of the star or with the interstellar medium. So here there are 2 absorptions, and we would say that this is interstellar and this is related to the circumstellar medium of the star. And we did that in the 2 calcium lines where exocomets are classically detected, but also in the sodium lines, because sometimes you can also see variability in these lines. And when the differentiation between the 2 absorptions was not so clear, for example, in this case, you cannot see clearly, but there's also a gray line behind. So the interstellar medium velocity and the stellar radial velocity are coincident. We checked stars in the background. And we end up just serendipitously finding this, which is a star that was not in our sample, but has clear variability in the calcium line. So all of this led us to this. This is the results. So for example, we have 18 stars, but we see some kind of variability that could be related to this phenomenon. We also have other 14 stars, along with this 29, where we think the stable absorption present there, it's related to the circumstellar medium of the star, so there's gas around that star. And we also have other stars that it's very clear the gas is coming from the interstellar medium. Many of those are from the young associations. They probably have a bubble that and they're all in it. And we have 9 that we couldn't discern the origin, either because the radial velocities were coincident, or we didn't have any, or there were no stars that we could compare them to. And then we have 55 with no gas accidents at all. If we check this part here, we see that these are the stars that we detect to have variability. So 6 are new, so we can add them to the sample of stars with exocomets. And 12 are previously known, and there are also other 8 that were previously known stars with exocomets, but we do not see anything in there. That could be due to various factors. Either there's no activity in the star or no exocometary activity in the star when we were looking at it, or we have different resolution. So it's nothing to worry about. Well, this 6 is the 5 stars in our sample plus the other one we found. And when plotting this in a color magnitude diagram, we see, well, that the stars that are earlier types have higher rotational velocities, but also that's where all the stars with variable absorptions are, and with the circumstellar absorptions. So we do see a trend with the spectral type, let's say, and the presence of exocomets. This is not surprising, because as I told you before, all exocomet host stars are A-type. And we can also see that the same here. There's a difference between the when histogramming all the objects in radial velocity and just the ones that have some kind of absorption that is not from the interstellar medium. They have higher velocities. We have a lot of objects with very low rotational velocities that do not have anything. But when comparing the stars that have a circumstellar origin, the absorption, or interstellar, or we don't even know, they're indistinguishable. And we also check the ages of these stars because we expect them to be young, but we didn't find a trend. So these are some of the associations we have in our sample. For example, we have a lot of stars of Upper Scorpius, and most of them have interstellar absorptions, but we also have some older stars that do have exocomet-like activity. We don't have any as old as Eta Corvi, the one that was an F-type star with a 2.9 sigma detection. And from this work also came out this work first, where we checked all the stars that had a bright debris disk, bright debris disk, and cold gas detected. So either in far infrared or in submillimeter or millimeter ranges, and we checked them in our photometry. And what we saw is that, this is not clear, that the ones that we could attribute to the interstellar medium, to the circumstellar medium, they all have edge-on inclinations, or close to edge-on. And the ones where we didn't see anything, they're close to face-on. So we can add here beta peak and formalhaut because they're not in our sample, but we can study them. And we found that this was due to a geometrical effect. So let's say that it doesn't matter when you look in the submillimeter or millimeter range to the gas, the cold gas, because you will see it anyway, independent of the orientation. But if you're seeing in a spectroscopy, you need the star to be, or the system to be edge-on. So the gas will transit the star, and you can see the absorption. And we also found one star with a lot of variability. This is the first thing we published because it was really, really highly variable. And we can even say that it's only second to beta peak in variability. So all the stars with exocomets we have found do present variations, but not as much as Beta Pictoris, but this one does. It varies, you can see here, within hours. And it's also particular of this star that it's very old, but when put in a sample, not really much different than the other ones. And, but it lacks a debris disk. This star was selected because it has evidences of circumstellar gas, but we don't have any evidence of a debris disk. We didn't have back then, and we don't have now when we checked in longer wavelengths because there were no studies. So what causes this variability? Well, the star is Filio, I think I didn't mention. Could be exocomets, but we're not quite sure yet. So we're just keeping on studying this star. I hope we will publish something more soon. And another interesting result from the sample is this star. HR10 was one of the classically exocomet host star. So it was one of the most famous ones, along with Beta Pig, AT172555, and so on. And we observed this star first with Mercator in La Palma, and then we ended up doing a follow-up on this object because we see that the observation, or the absorptions indeed have variations, but when fitting the two, let's say the two absorptions, we can differentiate a deep one and a shallow one. We found that this was not due to exocomets, but it rather was a binary star. So it's a binary. Both stars are A-type stars. Here are the orbits, and they're very close. There's like 2 AU of separation, but both of them have a circumstellar gas that was we detected in spectroscopy. So I will sum up, and I can say that we have 6 new stars with variability that were not reported before in the literature, and that we detected 18 stars with FEBs. But the data we have now, it's so far from the data we have from Beta Pictoris. So these stars definitely need follow-up. We have detected around 60 stars with narrow absorptions. And when checking the narrow absorptions, we found that around 32 have a circumstellar origin, so we can say that there is gas around those stars. And we have published 3 papers that I just told you. So we found also that there's a geometrical effect in the disks, and that favors the detection of gas. We found the huge amount of variations in Filio that we definitely need to study more because they look like exocomets, but it could be something else. And we found that HR10 is not an exocomet host star, that it's rather a binary, so we have to be careful now that other sources that we don't expect, for example, we were checking activity from the star and so on, or winds, but we didn't expect this kind of things to happen because we don't expect 2 stars so close to have both a circumstellar disk. And that was quite fast, so I'll thank you and have some questions.
Thank you, Isa. Thank you, Isa. And questions?
Thank you for the talk. In the case of debris disk, how can we know if the absorption line is due to the, for instance, a dusted bell orbiting the star, or in the case of debris disk, how can we know if the detection of the absorption line is due to an exocomets or, for instance, dusty bells, dusty rings orbiting the star? No, I think it's difficult to distinguish these 2 options.
Dust in the spectroscopy, we see gas. So it could be other thing outgassing. What we can say is that the gas is transiting the star, and it's sporadic and it's non-periodic. So we can't do a follow-up. Even in the case of Beta Pig, where you have so many events, you cannot do a follow-up of the individual events. It's very hard. So we really don't know what these bodies are like because we don't see them, like we don't have image, but we see that they have something that is evaporating. So what resembles to is comets in our solar system. That's why exocomets. But for example, in the case of white dwarfs, it is said that may be planets disrupting because they're close to a star, or they come into the tidal radius, or some other mechanisms. But yeah, it's just the analogy just comes from the features we see.
Also, in the case of debris, there are a lot of material, debris, for instance, dust and gas, grains. It is difficult to detect these features in optical because I think that the absorption would be very high, the extinction in this case.
Well, we only see them in the calcium lines mostly. Yeah. Calcium is optical. It's 3,900 angstroms, so it's optical range. And there are some detections in other lines in the ultraviolet, but so far the largest amount of detections is in the optical.
Okay, the observations up to now, the detections has been in the optical, in the calcium 2HK, right? But are they expected to be detected in some other lines, in some other elements?
Also detection in some sodium lines for some cases, and in ultraviolet, in the iron lines in the ultraviolet, and I think also carbon and oxygen, but we don't have many ultraviolet observations because it's, yeah.
This carbon, oxygen, are all these in the ultraviolet?
We don't see variations in oxygen lines in the optical range or in the near infrared that I know.
Periodicities, clear periodicities of these events? They are none. Why not? Understood why we don't see periodicities in an exocomet which is orbiting a star.
Well, it is not clear how you would distinguish or characterize an object just for one absorption that even varies with time. If you see, just a minute, the videos of the beta peak variations. So you see an absorption here, but just for that you cannot characterize the object and say, well, it has this orbit, this velocity, this size, and see if when it comes again it's the same object. So you cannot really say they're periodic. Actually, when they were called falling evaporating bodies, FEBs, that was in the 80s, because nobody would believe that they were exocomets. So they were called so because it was expected that some of them would just be destroyed or fall into a star. So there is no way to determine if you have a body that is coming around or not.
So why are these features only observed on A-type stars? Is there a physical reason or some kind of observational bias, or what do you think?
In photometry, until this year, there were no detections of exocomets around A-type stars. Also because A-type stars are not usually observed continuously in photometry. You cannot see planets around A-type stars in photometry, right? So it is not clear whether if it's an observational bias, because lines in A-type stars are wider and let's say you have less features. And when you see the calcium lines in, for example, a G-type or a LATEF, even, there's a lot of lines in the calcium overimposed to the calcium line. So it's very tricky to distinguish some variability there. But still, it could be a physical bias. There's a paper that goes so it's definitely not clear.
Following some comments by Mayra, I would say that you cannot claim that in the DC chemically polluted white dwarfs you may have a detection of exocomets, because in those cases they are expected to be surrounded by debris disks, which are probably not smooth, and so you are going to see some flickering in the light curves, which are due to this dust disk.
So exocomet was one of the explanations for debris disks. So it's not clear that it's exocomets. So
for the reason for the chemical pollution of those stars, but now it has been put away. The thing is that those stars are very hot. If you have a comet which are very close orbit, it's going to be disrupted and evaporated very quickly.
Deeps in white dwarfs could be also related to disruption of bodies that come very close to it, and so it might have nothing to do with this. But yeah, I just wanted to mention. But thanks. Yeah.
Yeah. Thank you, Isabel. You mentioned that you are seeing an absorption of the calcium line by gas. Do you have any means to constrain the gas which is absorbing the radiation in that wavelength? The amount or the gas? Which gas? Is carbon monoxide, dioxide, water? I don't know.
Calcium. So I mean, yeah, there's no molecular absorptions detected related to exocomets.
And also sodium.
And sodium. So
That you can see other metals, but
solid refractory material of the body. Yeah.
Refractory, so not volatiles. Yes.
And the amount?
At the amount, it's very tricky to say. For example, the column densities you can say, but it's very hard to estimate a real amount because you don't know how much calcium should be in the disk, or I don't know. It's a bit tricky.
What about the sun? Has anybody looked at the sun, at the calcium line in the sun, and correlated with an image of SOHO, for instance, with showing an evaporating comet, to see whether there is absorption there? Or
calcium lines are interesting in the sun just because of the activity, right? But there's reported, I think, one case of a comet that came really, really close to the sun, I think 0.1 AU, and that it evaporated calcium. You could see calcium in there, but you could not see the normal absorptions from the comet, like water or CO. Those elements were probably gone way before then. It came so close. So when it's really, really close, you can see the same line you see here.
Hello. My question is about that figure. Why do we see some displacement always at the material moving away and nothing on the left side of the material coming? So, I guess you will have a kind of random distribution, or why that pattern occur?
Let me see here. So if this would be the red, right? So you have a comment towards the red. But if the orbit is this way, let's say you would start to evaporate around here. But if the orbit comes this way, you would again start to evaporate this here when you cross the line of sight. So it's more likely that evaporation comes always when you cross the line of sight towards the red. So it's a bit tricky, but you could have some on the blue, but you expect to have more on the red, just because of geometry. Because if the object comes around here, you can have some blue detections, but if the orbit is not the right one, you wouldn't evaporate until you're really close.
Okay. I think I had to think about the geometry, because what we are observing now in the helium line of some exocomets, of some exoplanet. And what we are always seeing in the hydrogen and helium is really a very blue component, very large, and very little of the red, so which is just opposite to what you found. So I had to think about which is probably that the geometry one. Okay. No, there are many. Yeah, but at least QOP 69 and H189, 208. It's many of them, and all of them are really to the blue in the hydrogen Lyman alpha and also the helium triplet. Okay.
I have a comment. Can we are talking about comets because we are thinking in an evaporating gas going out from a body. But if this body is really large, like a trans-Neptunian body, we cannot say that this is the same case. If this large body like Pluto is going close to the star and evaporate a lot of gas, we will say that this is a comet. I mean, we cannot differentiate between a comet and a planet going.
Right. You see that there's a body that it's transiting sporadically, that it's not periodic, and you see it evaporating. If you had a planet, I know there's planets that are evaporating, like at least one. You see periodically, because it has like a stable orbit. If you had a body that is larger than the ones we call comets in the solar system, I think you would know. It would probably disrupt at this distance. It would just disrupt, and then you would see how the pieces evaporate or sublimate.
What happens if we have a periodic planet with outburst? This outburst that will be periodic. Will have the same depth.
Which kind of material is that? Because do planets eject metallic material? Refractory material?
The Enceladus is a
but it's water or CO. Yeah. So I don't know if we
put the sun. Everything. Maybe you.
The scale. Those comets are those bodies are very close to several stellar radii.
Yeah, you can. But it would just, I think.
At that point, you don't get any ice anymore. You have all the refractory material.
Yeah.
You only have atoms. Any kind of molecules and like that is not there, because the radiation field is so strong.
Any other question?